as we're getting going here, go ahead and look at the objectives for today. First one is explaining how to identify when an object is accelerating. So that's actually connected to our second agree-disagree statement there, right? And then calculate average acceleration. That connects to our first statement. And then the last one is to be able to read a speed time graph. We've already done distance time. Now we're going to do speed and time. Let's start by defining what acceleration is. Okay. Acceleration is a measure of the change in velocity of an object over a period of time. So when we were measuring speed and velocity, we were measuring a change in distance over time. Now we're measuring a change in velocity over time. Who remembers what velocity is? So speed is part of it. And direction. There we go. Speed and direction. Okay? Which means that to change velocity and to accelerate, you can either speed up. Okay? This is the one that makes sense to most people's brains, because when we think about a car and people talk about accelerating a car, they're talking about speeding it up, right? But did you know that slowing a vehicle down is also a form of acceleration? Okay, because it is a change in velocity. You're changing the speed at which the car is traveling. Speed is part of velocity, so when you change it, you change your velocity, and we consider that acceleration. Sometimes you will hear people describe these as positive and negative acceleration. So positive acceleration being speeding up, negative acceleration being slowing down. But there is one more way to accelerate based on our definition of velocity. Can anybody tell me what they think that might be? Yeah, you are accelerating even if you are just changing direction. So even if your speed is constant, if you change direction, that means your velocity changes. And because our definition of acceleration is a change in velocity, that means changing direction counts as acceleration. So basically, we can accelerate when we change our velocity. Next, we need to learn how to calculate acceleration. Okay? We use this equation. Average acceleration is equal to the final speed of an object minus the initial speed divided by total time. Okay? You may occasionally see this written differently. Okay? I am going to use the formulas that I am familiar with. So usually I will write it as acceleration is equal to velocity final minus velocity initial divided by time. Okay? And because sometimes you're given a starting time or an ending time, you might also see me write it as time final minus time initial. Okay? So you may see me write this equation this way. That is what those symbols mean. The little subscript F stands for final or ending time. The little subscript I stands for initial or starting. Okay? We are going to practice using this together, and then you'll do one on your own, okay? So to start with, we have this. A bicyclist started from rest along a straight path. After 2 seconds, his speed was 2 meters per second, and after 5 seconds, his speed was 8 meters per second. I see there's a typo there. It should say 8 meters per second, not 8 seconds. What was his average acceleration during the time from 2 seconds to 5 seconds? Okay, so in order to solve this problem, we have to start by finding our final speed. What was our final speed? 8 meters per second, okay? And we're going to subtract from that our initial speed. Now this is a little trickier because there's technically, they gave you 2 other speeds in this problem, okay? They told you that at 2 seconds, the speed was 2 meters per second, and then they also told you that to begin with, they were at rest, which is what in terms of velocity? 0 meters per second, okay? So to answer which one of these we're going to use as our initial velocity, we have to look at the last line. What was his acceleration during the time from 2 to 5 seconds? So that means our initial velocity is going to be the one at 2 seconds. So how fast were we traveling at 2 seconds? 2 meters per second, okay? And then we need to find our time. So our final time was at 5 seconds, and our initial time was at 2 seconds. So now we get to do the math. We're going to start by taking 8 meters per second minus 2 meters per second. 6 meters per second. And then we're going to divide that by 5 minus 2, which is 3 seconds. So 6 divided by 3 is? 2. And then the unit should be, any guesses? Close.
Meters per second.
Meters per second squared. Okay, this is a new unit because we divided meters per second by seconds. We're going to wind up with the unit meters per second squared. Okay, you might also see this written instead of with the exponent up there. You might see it written as a little caret sign and then the number 2, because not every computer allows people to put a superscript or an exponent up on top of that. So you might see it written with that little caret symbol instead. Okay. In fact, when you do your homework, Google Forms does not allow you to put exponents in, so when you're putting this unit, you'll need to use the little caret. Okay, now that we have done this, I want you to attempt the second problem underneath this one on your own. All right. The next problem says Aiden drops a rock from a cliff. After 4 seconds, the rock is moving at 39.2 meters per second. What is the average acceleration of the rock? Okay, so I'm gonna pull up a blank slide so we have more room to write than what's on here. Okay, so going back to our formula, we remember acceleration is velocity final minus velocity initial over time final minus time initial. Okay, so we can go ahead and fill in some gaps. What did we start at? We started at rest, okay? And that is critical information because starting at rest means both our time and our velocity are 0 when we start, okay? So we can go ahead and fill those in, right? Velocity final would be velocity initial would be 0 meters per second, and time initial would be 0 seconds, okay? Then what was our final velocity? Velocity, 39.2 meters per second, okay? And then how long did it take us to reach that speed? 4 seconds, okay? So essentially, because both our starting velocity and our starting time were 0, we just need to take 39.2 meters per second divided by 4 seconds. When we do that on our calculator, what does it come out to? 9.8 meters per second squared, like the inclusion of the unit there, okay? Which, coincidentally, this is the acceleration due to gravity, and it's actually the rate at which all objects accelerate towards the surface of the earth when they are dropped. Rocks, books, people, all accelerate at this rate. All right, that ticks our second objective, which was to learn to calculate average acceleration. Okay? There are 2 problems on the homework where you will have to calculate average acceleration. So if you get to those problems and you go, I can't do this, please do not guess. Please ask for help. Okay? All right. We're going to move on to our last objective, which is being able to read a speed time graph. Okay? Just like distance time graphs show speed, speed time graphs show acceleration. Okay? They are similar, but not identical. So, what's going to happen is we are going to compare things from a distance time graph to a speed time graph. The same thing, but showing how it looks different on each graph. Let's start by talking about an object that is at rest. Okay, so at rest again means not moving. On a distance time graph, what did it look like when an object was not moving? A flat line, okay? It's similar but not identical on a speed time graph, okay? So, distance time, flat line, anywhere on the graph, even if I drew it here, would still be not moving, right? Because the y-axis is measuring distance. So the fact that this line is not increasing or decreasing means that the distance is not increasing or decreasing. But the same is not true of a speed time graph. Notice that the y-axis on a speed time graph is speed. So the only way to show that an object is not moving is to make the speed value 0. So on a speed time graph, only a horizontal line at 0 means it's not moving. If I were to draw a horizontal line up here, this object is moving because it has a speed value. See? So it's moving up here. But at the bottom, at 0, that object is not moving. Okay? Now, let's talk about instead a constant speed. On the distance time graph, what did it look like for your object to be moving at a constant speed? A diagonal, right? A straight diagonal line. Okay? On a speed time graph, it's a little different. So remember that on this distance time graph, this line is at a diagonal because both time and speed are increasing. Or sorry, not increasing, but time and distance are increasing. There we go. At the same rate, which means constant speed. You're traveling the same distance for the same amount of time, so your speed is constant. Over here, remember that this line is now speed. So you can imagine that along this line, we would have 0 meters per second, 1 meters per second, 2, 3, 4, 5 meters per second. So any horizontal line means that that speed is staying the same over a period of time, which again means constant speed. So these two graphs are representing the same thing, but they're representing it in different ways. Now, what about increasing speed, speeding up? How do we show that on a distance time graph? Yeah, there was a line with a slight upward curve to it, okay? Because the distance was increasing at a faster rate each time, which means your line develops a curve. On this one, in order to show speed increasing over time, we just need to draw a diagonal line. Okay? So notice how easy it becomes to confuse speed time graphs and distance time graphs. So you always want to be looking at how these graphs are labeled before you try to interpret them. All right? This last one we did not talk about when we talked about distance time graphs, but on a distance time graph, if you want to show an object slowing down, you're still drawing a curved line, but you're going to draw it opposite, so it's going to look more like this. The distance traveled gets less and less for each second. And then on a speed time graph, you're going to draw this angle down. On a distance time graph, what did a downward sloping line mean? It meant you turned around and went back in the direction you came. All right? Because they were showing distance, they could show direction just a little bit, forward and backwards. On a speed time graph, we're only showing speed and time. So unfortunately, speed time graphs do not possess a way to show changes in velocity due to direction. There's no way to use a speed time graph to tell if somebody has changed direction, only if they have sped up or slowed down. Okay? If you want to know about direction changes, you'll have to use some other method to give that information to people. A speed time graph simply won't do it. This is the end of your notes for today.